Hello, my name's Nolan, and I'm going to give a 5-minute overview on our NeurIPS paper, Don't Be Lazy. CompleteP enables compute-efficient deep transformers. The TLDR is that we introduced CompleteP, which offers depth-wise hyperparameter transfer, fewer flops to reach the same loss with deeper models, and a larger range of compute-efficient width-to-depth ratios. First, let's start with the problem. So if you want to train a very deep transformer, the first thing is that deep transformers are unstable, and this kind of introduces risk into large-scale runs. Second thing, as you vary depth, models will not share the same optimal hyperparameters. So you're going to need to retune things or just make bad decisions. And the third is that deeper, narrower models are not competitive with shallower, wider models. So everyone just sort of uses width to depth ratio of roughly 100. There have been a few proposals for infinite depth parameterizations for ResNets. So first, consider the form of the ResNet that we have in this equation. So h of L plus 1 equals h of L plus f of L. But we have these green terms, L to the negative alpha for the forward pass, and then L to the alpha minus 1 to multiply the learning rate. So these green terms are what can implement an infinite depth parameterization. But we need to set the value of alpha. So Yang et al. Argue that setting alpha to 0.5 is best in practice, and also that depth-wise hyperparameter transfer is not possible for any alpha. And several works have adopted this alpha half prescription in practice. Bordelon et al. Find that setting alpha equals to 1 allows for better learning as L, or depth, goes to infinity. In this work, we're going to study these two promising candidates, alpha half and alpha 1. We find that only alpha equals to 1 ensures depth-wise hyperparameter transfer. So here we just have the x-axis is learning rate and the y-axis is loss. And we've trained models for 2 layers all the way up to 128 layers. And you can see that only the CompleteP parameterization, or alpha equals to 1, allows the same optimal hyperparameters to be shared by every single depth. Beyond transfer, in this work, we also study compute efficiency of deep transformers. In the plot on the left, we have the x-axis is the width to depth ratio, or n to L, and the y-axis as the loss increase relative to some very compute-efficient scaling law. The different lines correspond to different parameterizations. So green is CompleteP, blue is μp, and orange is alpha half. As you move to the left, or in other words, get deeper and narrower, CompleteP's advantage over μp and alpha half grows. In other words, CompleteP enables more compute-efficient deep transformers than μp or alpha half. In the plot on the right, the x-axis corresponds to the number of non-embedding parameters, and the y-axis corresponds to the width-to-depth ratio. The shaded area corresponds to the range of aspect ratios that are within 1% of the optimal loss achievable for that parameterization. You can see as we scale the parameter count, the blue area for μp shows that you want to go wider and shallower. Whereas if you look at the pink area, CompleteP, you can see that as you scale the parameter count, we can stay much deeper and narrower than μp can stay while remaining compute efficient. Now that we've looked at the empirical results, let's get into how CompleteP works. So both alpha half and alpha 1 stabilize training dynamics. In this test, we look at the activation norm of the final residual stream, h of capital L. On the very left column, we have the standard parameterization, or μp, or in other words, there's no depth scaling. And we find that as you scale the depth of the network, the activation norms at the final residual stream are going to be exploding. If you also test alpha half from literature for a transformer, you find that alpha half also has exploding activations. But with our derived corrections for the bias learning rate and the layer norm affine parameter learning rates, you can find that alpha half is also able to stabilize training dynamics. And finally, we find that CompleteP, or alpha 1, stabilizes training dynamics. We've shown that multiple alpha values can stabilize training dynamics. So how do we theoretically explain the success of alpha equals to 1? Let's start with a minimal example, a ResNet with a 2-layer linear MLP block. If we consider delta h of L plus 1, the change in h of L plus 1 after a weight update, we can Taylor expand this delta h of L plus 1 term. And you can note that the first order term of the Taylor expansion has a scaling proportional to L to the negative 1, whereas the second order term is L to the alpha minus 2. Our desiderata 3 that we add, complete feature learning, is that for all layers, we want the higher order terms to have the same asymptotic scale, even as L goes to infinity. Only alpha equals to 1 will ensure this complete feature learning desiderata. Thus, we call it CompleteP. Alpha equals to half, on the other hand, will actually have vanishing higher order terms, or be lazy with respect to the first order term as L goes to infinity. To summarize, the benefits of CompleteP are stable optimal hyperparameters across depths, significant flop savings over μp for deep models, complete feature learning, and a very easy implementation. It's just 2 lines of forward pass code. Here are the references. Thank you very much.